Hi guys, Problematic here with another short Unity video, and today I wanted to talk about implementing bullet time for your game. If you've seen the movie The Matrix, bullet time is when everything slows down and the main characters can dodge bullets and do other crazy stuff in slow motion. And that is actually really easy to implement. So let's get started by creating a new script called bullet time. And in that script, we're going to define our public API as a float saying what percentage of real time the slow-mo is. So we're going to say public float min time scale, and we'll default it to 0.5, which means that in our slow-mo, in our bullet time, we're running about half as fast as if we were running in real time. If I had set this to 2, that would mean bullet time was twice as fast as real time, which is cool but not very useful as far as gameplay goes. And then we'll have a private member called bool is bullet time to tell us whether or not we are currently in bullet time, and that'll default to false, so the game will start in real time. To trigger that, we're going to want to use a toggle, just like we did last video. We'll say if input get button down, and I've created an input axis called ability. You can do whatever you want, but I've created one called ability. The first thing I want to do is toggle bullet time, so is bullet time equals not is bullet time. And then we want to use that to tell us whether we should be setting our scale to this min time scale, our bullet time speed, or to real time. So I'm going to use a ternary operator with time.timescale, which is basically what percentage of real time the game is running in as we modify that. So we'll use a ternary operator with is bullet time as our condition, and if it's true, we want to set our time scale to this min time scale that we've defined. Otherwise, we want to set it to real time, which is 1. So that's the basic start. So before we do that, let's add a Gui element so that we can see what our time scale is. So we'll do GUI.box. We'll pass it a new rect. And I want to put this in the bottom right corner. So I'm going to say screen.width minus, say, 150 for room for the box. Screen.height minus 50. And then we'll say the width and the height of the box are half of those values. So 75 and 25. And then we'll pass in a string. Time.timescale.toString, because time.timescale is a float. And so let's save that, go back over to our editor, and we'll create actually a new game object, and I'm going to call it game controller, and drag bullet time onto it. So you can see our min time scale there. And the reason that I created a new object instead of just putting it on, say, my first person controller is that how fast time is running in the world is really kind of a global concern. The player might be able to trigger that, but there also might be enemies or special events that trigger bullet time as well. And so to avoid duplicating code, we'll put that in one globally accessible place called this game controller. So let's go ahead and start it up. And I've created this ramp. You can see in the bottom right corner it says we're currently running at 1, which means we're running in real time. So I've created this ramp that we can jump off. So I'll jump and then toggle, and you can see how we slowed down. It says we're now running at half speed. You can see how everything looks twitchy, so let's go ahead and fix that. And the documentation says that when you modify time.timescale, you also want to modify time.fixedDeltaTime by the same amount. Fixed delta time is how often things like rigid body physics are updated, and that happens in a fixed update, and that happens every fixed delta time seconds. The default is 0.02. So we'll just multiply 0.02 by time.timescale. And if we save that, go back over and fire it up again, we'll hit bullet time. And you can see we're still slow-mo, but things are a lot less jumpy because now our rigid body physics are operating on the same scale or the same magnitude as the rest of the game. So that is basically bullet time, but there's a couple other cool things that we can do. So let's jump back over to our code, and it's cool that we can hit our ability toggle key and move from bullet time to real time, but it would be cooler if when we hit the toggle it wasn't an instant transition but happened over, say, a second or 2 seconds or whatever time period we define, so it kind of slides into slow-mo. I think that would be cooler and more cinematic. So the question is, how do we accomplish that? And if you're thinking about it at a high level, you might say, well, I'll do it in a loop. I'll start at 0 and loop until we hit 1 second, and over that time kind of slowly transition our time scale. And so you might write it something like this. You say float t equals 0, our starting time. You say while t is less than or equal to 1 second, we want to add some arbitrary amount to t. So t probably plus equals time dot delta time, or the times that's passed since the last frame. And then we want to have some number between our start and our end. And let's define those. So we have a float start scale, which is just the time scale when we started the transition, and a float target scale, which is the same logic that we use here. So if it's bullet time, our target scale is our min time scale, and if we're not in bullet time, our target scale is 1, or real time. So we want to, based on t, set our time scale to some value between start scale and target scale. The way that we can do that is with a function called Mathf.Lerp, or linear interpolation. So it takes a from value, a to value, and some value t that, if you look in the documentation, is clamped between 0 and 1. So if you tried to pass 50 to it, it would still give you 1, and that would give you back your to value. It's basically a percentage between from and to, right? So if you had a from of 1 and a to of 5, and your t was 0.5, you would get back the average of those values, which is 3. So we want to lerp, or linearly interpolate, between our start scale and our target scale by t, and we want to assign that to time.timescale. So if you're thinking about it, that looks like it would work. But the problem is this update method happens in one frame. So our loop is basically wasted because it's going to loop over and happen instantly. So our transition is going to happen all in one frame, and the slide effect, the cinematic transition speed, is going to be lost. So how do we solve that? The answer is by using coroutines. And a coroutine is basically a function that can yield back to the main thread and say, hey, pick me up later, and I'll just continue from where I left off. So let's define one of those. And coroutines require a return type of IEnumerator, and we'll call it toggle bullet time. And in toggle bullet time, we're essentially going to do what we defined here. So we'll just cut all this out and put it here. And then instead of our transition, we want to call our coroutine. We do that with the start coroutine method, and we'll pass it the string method name, toggle bullet time. Now you can pass it the method itself, but the reason that we're passing the string now is because if you pass a string, you can also stop the coroutine. And the reason we might want to do that is, picture this. Your player is playing the game and he toggles his bullet time on, and then halfway through our transition, he toggles it off again. Well, because he's hit that toggle twice, this coroutine is starting twice, and so you have two kind of conflicting code paths that are both trying to speed up and slow down time at the same time. And the universe probably won't explode, but you'll get weird behavior until things level out. So the way to stop that is to just stop the problem before it starts and call stop coroutine toggle bullet time before we start it again. So that way, if we're in the middle of the transition, we'll just say, hey, forget that transition, and transition us back in the other direction. So this looks like a pretty good example, but there's one more thing that we need. This IEnumerator needs a point to tell it, hey, okay, I'm ready to go back and give execution back to the main thread or to the main update. And the way that we do that is with the yield keyword. And in C# it's a little belabored. We have to yield return null, and that basically says when we hit this point, just go on back to our main thread, and then in the next frame, just pick right back up from here. And the cool thing about that is that this state, so our t and our start scale and our target scale, they don't get reset because we're yielding and returning inside this while loop, and so all of this remains the same as it was before. Whereas if we were trying to do this, we could do it in the update function, but we'd have to put put this t on the class, and we'd have to put our start scale and our target scale on the class, and it just gets a lot messier. And so this is a really clean way because we can do this inside of a loop. So let's save that, head back over, start it again. So what we should see is our speed here transitioning from 1 down to 0.5 over 1 second. And you can see that that happens. Now we transition back up. So if you'll remember, I said that lerp clamps t between 0 and 1. So if we wanted to say make a public float transition speed and say we wanted that to happen over 2 seconds, the problem is if we came here and say while t is less than transition speed, then basically anything greater than 1 is going to be lost, and it's just going to say 1. And so our timescale will do weird things. And this is a mistake that people commonly make with Lerp, is that they try to use it like with time, time.time or whatever, and so it only behaves as expected in the first second of gameplay, because after that, this t value is greater than 1, which means it just gets clamped at 1 and you get the from value or your target value out every time. The way we can solve that is with math. Let's put our transition speed back to our while condition back to 1, because again that's the maximum that Mathf.Lerp lets t be. And then we can say something like delta t equals time dot delta time times 1 over transition speed. So now there's still a problem with this, and the problem is that time dot delta time is affected by time dot timescale. It turns out almost everything in the game is, except for one value that we can use to kind of keep track of delta time by ourselves. So let's say float last tick, or the last time that we ran, equals time dot real time since startup. And that is the only value on the time object that is not affected by our time.timescale as we iterate through. So our last tick equals that. So we can say, instead of time.delta time, we can say time.realtime since startup minus last tick, and then we can update our last tick value to equal time.realtime since startup. So that lets us have a time independent way, because we want to transition over 1 real second, right? 1 second from the player's perspective, not 1 wacky second as time slows down, then seconds get longer. We don't want to deal with any of that. And so using real time since startup is a good way to make that independent of any modifications that we're making. So let's pop back over, start this up again. We should see this transition over 2 seconds. So hit it, and it does. That is great. So we can set now our time scale to be really anything that we want, and we can transition over it. So the last thing that we need to do is, again, you see that it's jumpy. We need to come back over, and at the end of our loop, we need to say time.fixed delta time. That is not fixed delta time equals 0.02 times time.timescale, so we'll keep our fixed delta time in sync. So transitioning between slow-mo and real time over a period of time is kind of a contrived example, but hopefully this has given you an idea of the kind of power that you can harness in coroutines. You know, if you're trying to fade a user to invisible because they have a cloaking device, this is a great way to do that. Also, if you have things that need to happen frequently, but maybe not as frequently as update, because update happens every frame, so it's happening potentially hundreds of times per second. If you have something that's more expensive, it needs to happen frequently, but not so frequently as update. A coroutine is a good way to do that, because you can yield and return a new object called instead of null, a new wait for seconds, and then you pass a float how many seconds to wait. So if we wanted to call it every 1/10 of a second, instead of, so if you return null, your coroutine is going to be passed back into every frame, but this is going to say, hey, don't bother passing back into me until 1/10 of a second has passed. So that lets you do things on a constant basis, but not quite as quickly as update. So I hope that's been helpful. That is how you can implement bullet time in your game, and that is a good start down the path of how you can use coroutines to harness more asynchronous behaviors. Thanks for watching.